Okay, so the topic that we're going to be getting into now is Chapter 8, and this refers to internal flow. So, what we essentially got is a pipe, and the pipe has fluid flowing through it. So, here's the inlet, which is what we're talking about right here, and the fluid is going to move through the, the pipe itself. So what we're assuming here at the inlet is that the fluid is coming in through a nice rounded inlet. It's not a very nice rounded inlet, but the idea is that as fluid, it could be a little turbulent here, but as it comes in through the inlet, it eventually, just before it's entering the pipe that we're considering, it'll have more or less a uniform velocity profile. So that's what we're assuming here. So what we got in this situation is we have a uniform flow coming into the pipe, and right away, once this material assumes that it sees a wall, the boundary layer is going to start growing. All right. So the shapes that are being shown here is, again, this is right out of the textbook. So they're showing the growth of the laminar boundary layer. So just like in external flow, the boundary layer will have a thickness, and what's happening as the boundary layer the size increases uniformly if we assume we have a circular pipe. So the boundary layer is going to start increasing and moving inwards until finally it coalesces so that there is viscous effects controlling the flow through the entire flow field from R equaling 0 to R naught, or sometimes they'll call this capital R as well, depending on what book you're using. So this period of growth of the boundary layer is termed the hydrodynamic entrance region. And I forget what they used in the Munson textbook, which would be the fluids textbook you used last year, but they're using X sub FD for fully developed, comma H for hydrodynamic. And once you have it fully developed, you have this typical parabolic profile. And for the discussions that we're going to be using, the Reynolds number is much the same as we've been using. Oh, sorry about that. What did I do? There we go. Move some things around. All right. So our Reynolds number for circular tube. Oh, come on. Stop doing that. Oh, I'm not in my pen tool anymore. Okay. Come on, pen tool. All right, now my pen tool is working. So when we're assuming a circular tube, the radius R naught, but that'll be diameter D, so that's the diameter of the pipe, multiplied by the mean velocity. What do they mean by the mean velocity? Well, we're going to get back to it, but that's going to be a very important term. But if we assume, let's go back to the original drawing, that if we have a known, oh, every time I move, my pen changes. Okay, but if we have a given diameter and I know it's a circular tube, well, then the area of the cross section in this case would be pi R naught squared, or pi over 4 capital D squared. Either one of those will work, but that'll give me the area of the cross section. So if I know the area of the cross section and I know the mass flow rate, and I know the density of the fluid, I can then define this term known as the mean velocity. And we'll be utilizing that. And then if we use a standard value for when the Reynolds number will allow us to be either laminar or turbulent, so the boundary layer is always going to grow and it's always going to coalesce. Right, we've discussed that in previous classes and the like. But what we're going to get here is that the boundary layer, the type of boundary layer, is solely dependent on the Reynolds number. So if I want this boundary layer, which is producing this velocity profile, if it's going to be a laminar boundary layer, the Reynolds number is going to be less than or approximately equal to 2300. So, and this is a real big range over here, right? So what we essentially say is as long as you're below 2300, you're going to be definitely laminar. And if you're above 10,000, you're going to be definitely turbulent. This region in between, again, just like we explained for our external flow, it's a transition region. So of course, some problems and some applications, you're going to be stuck to be in that region. But for solving or using our analytical solutions and our whatever correlations we come up with, normally we'd like to stay to this side or this side. We'd either like to know that we're fully laminar or fully turbulent. Okay, so this will define this value here, which is what they say. The textbook says the transition to turbulent is likely to begin in the developing boundary layer of the entrance. So I'm sorry, it says it somewhere that we'll just utilize this value of 2300. And the text will basically, if there's anything above 2300, you can assume it's turbulent. But I think most of their problems will try to make the Reynolds number for fully turbulent flow to be above 10,000. All right, so there's two different expressions for the hydrodynamic entry length. So for laminar flow, where the Reynolds number is less than 2300, the distance that you have to go from the entrance until you are fully developed, right, it's where the boundary layers are coming together, has this value. It's simply related to the Reynolds number. And since the Reynolds number, well, it can be less than 2300. So you have just a single dependence on the Reynolds number. Now, if you are going to be having a Reynolds number that's greater than 10,000, then you're going to have a situation where the entrance length, it'll be somewhere greater than 10 and somewhat less than 60, this ratio of the entrance length divided by the diameter. So it says, but notice what I have in the box here. For purposes of this text, we shall assume fully developed turbulent flow for x over d greater than 10. So what does that basically mean? It says that if you have a diameter, let's say you have a diameter equal to 5 centimeters, and your flow is, and your Reynolds number is greater than 10,000, so your entrance length, xfd, is going to equal 5 times 10, so 50 centimeters, or half a meter. Now, whether that's true or not will, of course, depend upon the actual physical situation. But again, for textbook calculations, that's what they're going to utilize. So now the next thing that we have is, and again, I can't stress this enough, the discussions that you have done in fluid mechanics typically focused a lot of time and effort on the laminar boundary layer. And again, why? Well, because the laminar boundary layer produces or allows you to generate some nice analytical solutions. So you have a nice analytical solution for the mean velocity. So we have function of the radius of the pipe and the viscosity of the fluid. And typically, since you know the mean velocity because you know the area of the cross section and you know the mass flow rate, you'll typically be able to figure out what the pressure drop is. So this is again one of those differentials where you're never really evaluating the derivative dpdx, but dpdx is the change in pressure as a function of x. So you have two situations. If you can measure this, you'll have an idea of the mean velocity, or if you know the mean velocity, you'll have an expectation of what the pressure drop is in the pipe. Then the other result coming from the analytical solution for the laminar boundary layer in a circular pipe is that you get this nice profile that goes from r equaling 0 to r naught, and it gives you this parabolic profile. So those are two results from the analysis. Now, but of course, remember that if we, I just have to insert a new slide here. Hold on. So if we are in a situation where we have a turbulent boundary layer, So let me go back to my pens here. Come on, pens. And we have our pipe. And if we have a turbulent boundary layer, what that essentially means is that we're at any given cross section, and what's essentially happening here is the fluid is swirling back and forth, right? It's all these vortices. And what's happening is you're getting a lot of mixing. So for a large extent of the cross section of the pipe, you're getting a fairly constant velocity. So it looks very flat in the front of it. But then as you get into the walls, you get this situation where the viscous forces dominate, and you'll get this sudden drop off so the fluid velocity is fairly uniform for a large portion of the fluid going through the pipe, and then as you get close to the wall, you get this very distinct and very quick drop off down to due to the no slip condition. So again, you probably looked at that a little bit in fluid mechanics, but there are just two very, very distinct profiles. The laminar profile has this very nice parabolic profile, and the turbulent profile has this it's almost rectangular with just these slight very rapid drop-offs, high gradients of velocity close to the wall. Okay, just to throw it up here, you have the Moody diagram. So once again, if you're given different types of information, if you know the pressure drop and you know the mean fluid flow, and you know that with that you can typically calculate the Reynolds number, and if you have all of that, you can go ahead and figure out what your friction factor is, and that'll give you essentially what your pressure drop is. So it's all tied together over here, right? So if you know your mean velocity, you can get your Reynolds number, and from your Reynolds number, you can go up knowing whatever your relative thickness is. That gives you your friction factor, and then you can solve for your pressure drop, which is typically what you're looking to do. Okay, so now we get into the heat transfer. All right, so just as there's a hydrodynamic boundary layer, there's going to be a thermal boundary layer. So in this case, it's being called DT, and just the same as you have an entrance, as the entrance moves in, the boundary layer, the hydrodynamic boundary layer is growing, but you're also getting an effect of the differential temperature between the surface and the fluid inside, and you're getting a change in temperature. Now, what's happening here, of course, is that, well, let's assume that the pipe is hotter than the fluid. So you're constantly getting an influx of thermal energy into the fluid. So what's happening here, while you're outside the thermal boundary layer, you're going to have a fairly flat temperature profile. And then as you move into the boundary layer, or conversely, as thermal energy has had time to transfer from the wall into the fluid, you start getting this profile. So there's a constant temperature profile as it moves into the pipe, and then slowly what we're getting here is the temperature is increasing. So constant temperature, and you have this increase in temperature. So once that temperature profile has been set, or the other way of saying it is all the fluid that's coming into the pipe has now experienced some type of temperature change due to the differential temperature between the wall and the fluid. So we refer to that as the thermal entrance region. All right, so one of the things to point out here in this diagram, because it's a cool diagram, but it takes you a while to figure it out, is that you have this, let me go back. Well, actually, I had it. I just moved the diagram before. Okay, let me put this back. There you go. All right, so what I was trying to show is that this graphic down here, this scale, is telling you that from here to here, this line is representative of what the temperature was of the fluid coming in. And this distance over here. So the line, length of this line is representative of what the wall temperature is. And then what you start seeing as you start moving, once you get the full effect of the thermal boundary layer, you'll start seeing that the temperature will start increasing. So this is the centerline temperature, and now the centerline temperature has increased a little bit more, and so on. Again, in this case, we're not exactly concerned too much about exactly the shape of the profile, but we want to understand what's happening to the overall or the mean temperature of the fluid. So there are two different surface conditions, a constant surface temperature or a constant wall flux. So let's take a look at what we're discussing there. So for a constant wall temperature, you have a situation to maintain a constant wall temperature while the temperature of the fluid is changing. So as you're moving into the pipe, right, the overall or the bulk temperature of the fluid is increasing. So there's going to be less heat transfer if you have a constant temperature wall, right? Because the temperature differential is what's driving the heat rate into the fluid. So as the mean temperature gets larger, the temperature difference, let's call it Ts minus T mean, is getting smaller and smaller. So what's going to happen here, as you move down the pipe, you would essentially, to create this situation, you would need to have different heater segments giving different Q values. And as you're moving down through the pipe, these Q values would have to keep decreasing to maintain the surface wall temperature. So I make the point over here that this situation is limited because after a certain point, right, the mean fluid temperature is going to reach the same temperature at the wall, and essentially heating will stop. So you'd have that kind of situation. So now the other situation that we can deal with, or that can lead to heat transfer to a fluid within a tube, is one where we maintain a constant wall heat flux. And again, we've talked about this in class, that this is the more realistic case where you essentially have a heating blanket that is wrapped around the pipe, and say the heating blanket is giving you, say it's a 3,000 watt heating blanket, 3 kilowatt heating blanket, and that would mean that it is so many watts per square meter, so that then you would get a constant heat flux. So that is probably the preferable way to discuss what's going on here. And all they're showing here is that there might be a slightly different heating profile. It's going to be the exact same thing. You're going to have a hydrodynamic and a thermal boundary layer growth, and that the growth and then the subsequent heating up of the fluid is going to be dependent upon a slightly different characteristic, in this case a constant heat flux. But you do have a situation where the mean fluid temperature can continuously increase. So this would be a situation where you might possibly actually have the fluid go from a set temperature all the way up to, say, if it's water, you could be at water at 0 degrees C, and then somewhere on the outlet you could be at high temperature steam or high pressure steam, and that would be a possibility for a situation where you had a constant heat flux. Now, of course, you could have the same situation if you had a constant temperature wall, if the wall temperature was high enough. But again, the same caveat goes that to have a constant temperature wall requires essentially a active control system to maintain or to control different heating elements so that you are maintaining a constant temperature wall. So the next lecture that we're going to be getting into, we'll actually be talking about the different types of correlations and how we go about this. But what we are going to have to decide upon is how do we define the mean fluid temperature. So in a given case, right, back to thermodynamics, we have Q, the total number of watts, is equal to m dot C sub P delta T, right? So we've started with that a long time ago. It's the first law. Heat in will, the heat energy in will reflect the total rate of change of temperature in the system. But in this case, it's not, right, in conduction, it was dt, which gave the time stamp. In this case, it's going to be m dot. M dot is kilograms per second. So that's where the rate comes from. But regardless of that, we are somehow going to have to decide how we bring about a mean fluid temperature. So in this case, the situation is going to be where we have a known m dot, a known Cp, and the definition of the mean temperature is going to be given by this integral. The integral is over the area, right? So this is almost one of those cartoon integrals. We don't really necessarily always have to evaluate this integral, but we're going to have a constant density. The u is going to be a function of the area. C sub p is going to be a constant, but temperature is also going to be a function. So if we wanted to be an integral over AC, it might be that this turns into an integral over R, and you would have U as a function of R and the temperature as a function of R, where we would integrate this from R equaling 0 to R equaling R0. And there would be a squared term in here because, right, the area is equal to pi r squared. So I don't want to get into that right now, but if we were going to do this, there's a way to evaluate this integral. Let me erase the material here. Wrong one. Come on, where's my eraser? Sorry. Having real problems here. All right, I'm going to not worry about that right now. And then lastly, once we would have the mean temperature, that is going to allow us to activate or utilize Newton's law of cooling, because we will normally know the temperature of the surface. Now, what do I mean by this? Well, essentially what we're going to know is that at the inlet of the pipe, we will know what the it's going to have a constant temperature fluid, and we will know the surface temperature. At the outlet, which is the other thing that we're really going to be interested in, we will know that we'll have some sort of temperature profile, and we'll be able to determine the mean temperature, and we will also know what the surface temperature is. So this will let us know what the total heat rate is, and that'll allow us to determine the heat transfer coefficient, or vice versa. What we're trying to do is we will be looking for what is this heat transfer coefficient. So that's one of the main emphasis of the rest of this chapter. So this little discussion was really just to give you an introduction to what's happening with regards to convection for internal flows, and we'll be getting into the meat of it, the actual analysis, over the next couple lectures.